Hey guys, thanks for joining us for another one of our webinars. It's been a little bit quiet here on HPA front. Ben and I have been flat out with some business things that haven't allowed us to bring you some webinars for a few weeks. Namely, we were at World Time Attack a couple of weeks ago over in Sydney, and we interviewed some really interesting people, had a look at some amazing cars, and basically enjoyed that side of motorsport. That World Time Attack event is getting better every year. If you are in Australia and you haven't been, you need to. If you're in another part of the world and you're looking for an excuse for a holiday, World Time Attack's a pretty good reason to head to Sydney. So we've done that. We've also been working really hard on finishing up our MoTeC M1 course, which is painfully close. We'll hopefully have the finishing touches on that this week, and it'll be a case of proofing it, and finally we can get that out. I've said it before, but I'm confident we will have that course out before the end of November, so that'll be really exciting for anyone who is transitioning onto that new MoTeC M1 platform. Now, while I'm talking about courses as well, Ben and I have got a very busy schedule of course creation scheduled for next year. Those of you who took us up on our VIP membership will already have a little bit of an idea of what we had planned. Now, of course, what we've got planned in the way of courses is still up for negotiation. Basically, we are here to serve you guys, our members. So if you've got something particular that you really want a course on, please feel free to email us. Probably best to email ben@learntotune.com. Let us know what courses you want, and that way we can make sure that we're providing the best courses, the most suitable courses for you. Now, the last webinar that we ran, we were telling you about our brand new all singing, all dancing website, which was due for launch today. As with just about everything in life, turns out that getting a website built, it's not as simple as you'd think. And as per usual, we've got a couple of delays, so unfortunately it looks like that's going to push out into December. It's really frustrating for both Ben and myself. We've really been looking forward to this website, and Ben particularly has been putting in hours behind the scenes making sure that that website is going to really deliver. So unfortunately, you'll all have to wait yet another month to see what we've got planned, but I know that you're going to be stoked with it. It's going to fix all of those niggly problems with the forum, the double logins, and all of that stuff that you guys have been putting up with, and we thank you for your patience. In terms of other updates, just a little bit of an update on our 350Z project. We have got some panels on that. It's back from having the cage installed. It's been painted. It's got a new windscreen in it with no cracks in it. If everything goes to plan, Ben and I will actually be having a chance to drive that on the track for the first time a couple of weeks' time up at Manfield. And we've also been lucky enough that YHI New Zealand's come on board supplying us a set of Enkai RPF1 wheels and a set of Nitto NTO1 tyres. So we're stoked with that. It'll give us a chance to get out and actually see how our ECUs are performing out in the real world. Let's be honest, we don't drive our cars on the dynos. Now, one last thing I wanted to mention, while we were over at World Time Attack, we caught up with the guys from MoTeC, and they've just launched their brand new Elite ECU. And while we were there, we caught up with Matt, and if you're interested in finding out a little bit more about what the Elite series offers, how it stands out from their existing Platinum series ECUs, if you jump onto our Facebook page, there's an interview that we shot with Matt while we were at the World Time Attack launch, and go and check that out. They were kind enough to actually give us one, so we've got one sitting here that we'll be installing in both our 350Z as well as our dyno test mule engine. So that's going to be coming up hopefully before the end of the year, so we can get a chance to demonstrate some of those advanced features. We know there's not a lot of these out there in the wild at the moment, so it's pretty cool to have one of the first handful that have been sold or delivered. Okay, so to get on to our topic for today, which is injection timing. First of all, before we get into it, I want to just discuss a little bit about the concept of injector timing, what it is, and what you need to know when you're configuring it. Also, how it can actually affect our tune, what the effect on both our air-fuel ratio as well as our torque measured on the dyno will be. Now, when we're talking about injection timing, what we're talking about is the point in the engine cycle where the injection event occurs. And now the very first thing to understand is there's two ways of describing the injection event. We can be talking about the injection event in terms of crankshaft degrees for the beginning of injection or the end of injection. So it's really important when you're looking at tuning the injection timing table in an ECU to make sure you have a good understanding of whether the ECU is programmed in terms of end of injection angle or start of injection angle. Now, generally, what we're really interested in is the point where the injector finishes its pulse, and that's called end of injection. So generally, for my little brain, that's how I make sense of it. I like to be looking at the end of injection angle. Now, the reason I do that is because that's a constant point, and we want to be able to time that in regards to the intake valve opening. And obviously, as our pulse width changes, as the fuel demands that the engine has increase or decrease, our injection pulse width will become bigger or smaller. Now, if we're looking at our injection starting point, or the angle where the injection pulse first starts, the end of injection angle will actually start moving around as our pulse width gets bigger and smaller. So that's why I like to work in end of injection angle, because it just makes more sense. It's a fixed point in time regardless of the size of our injection pulse. Okay, so now let's just jump onto my laptop screen here, and this is just a nice little diagram that I found from Comp Cams, which happens to give a reasonable explanation of what's actually happening with our intake and exhaust valve opening as we go through our engine cycle. Now, first of all, remember that there are two engine revolutions, 720 degrees of engine rotation for one engine cycle. So that's represented here. We've got TDC in the middle here, which is actually, that's the point where the piston's at top dead center between the exhaust stroke and the intake stroke. So if we start all the way back here, on our power stroke, as the piston moves down, again, this point at the left-hand side of the screen, this is top dead center. The piston's at the top of the stroke just after the spark event has occurred, and this is our power stroke. So the piston is moving from top dead center down towards BDC, bottom dead center, and somewhere near the bottom of the stroke, the exhaust valve opens, so that lets the spent gases, the exhaust gases, blow down and start expelling out through the exhaust system. So the piston's now at bottom dead center, and it starts moving back up the cylinder on the exhaust stroke, and this is forcing our exhaust gases back out, ready to start taking in a new charge of fuel and air. Now, somewhere near top dead center, before top dead center, we see our intake valve actually opens. Now, this point obviously is going to depend on your particular camshaft profile. Generally, that is going to be somewhere around about 400, maybe 420, maybe 390 degrees before top dead center here, which is the top of our compression stroke. So this is the same point, basically repeats over here because the whole cycle repeats. So that's the important point to note. Depending on our camshaft profile, our intake valve is going to be starting to open somewhere around about 400 degrees before TDC. So then we move into our actual intake stroke. The piston moves past TDC, starts moving back down the bore, and that's when we get our fuel and air charge is coming into the cylinder. And you can see again another point is the intake valve doesn't close at the bottom of the stroke. It closes quite a considerable distance after the bottom of the stroke, depending on your cam timing, as much as sort of 50 or 60 degrees after the piston started going back up the bore again. Okay, so that's what's actually happening inside the engine, and I've got another little graph here. You'll see this is the sort of information that'll often be provided with a camshaft, an aftermarket camshaft that you've bought. So what we've got here is the red line is our intake camshaft or intake lobe, and you can see it's relative to TDC. So in this particular, for this particular camshaft, our inlet valve opens 30 degrees before TDC, and then it closes 70 degrees after bottom dead center. And again, if we've got this sort of information, we're going to know exactly whereabouts in the engine cycle our intake valve is opening and closing. Okay, so that's the basis of what we're trying to or what we're going to be adjusting our injection angle to cope with. Now, there's two ways we can work our injection angle, and ultimately we're going to have a look on the dyno to find out exactly what the engine actually wants to see. With sequential injection, we've got the ability to control each injector individually and time it for the valve opening on that particular cylinder. So this is one of the advantages of sequential fuel injection. We don't get this advantage if you're using batch fire or group fire injection, and in fact the whole aspect of injector timing kind of goes out the window. So what we can choose to do is time the injection pulse so that it is occurring when the intake valve is open. Now, there's one advantage of doing that is we're going to make sure that we're getting all of the fuel delivered while the intake valve is open. So we're going to get less of that fuel wetting the back of the valve, wetting the port, and falling out of atomization. So of course with fuel, it's really important that the fuel is delivered in an atomized form. And if we're delivering the fuel as a puddle or a liquid, generally it's not going to burn particularly well. So if we time the fuel injection to occur when the intake valve's opening, that's going to make sure that our charge is getting into the cylinder in a finely atomized mist, and it's going to be easy to combust. Now the flip side of that is that's basically known as open valve injection. The flip side of that is there can, in some instances, particularly at light load, be some advantages in actually injecting against a closed valve. And the reason for that is when the intake valve opens, what we do get is a quite an irregular pulse or pressure wave across the tip of the injector. So basically the differential pressure across the injector is quite erratic. So in some instances we can find that we'll actually get a better result injecting at light loads and low RPM against a closed valve. Now the question I suppose there is, so how do you know what way to go? How do you know what your engine wants? So what we're going to do is look at how we can actually tune the injection end angle on our MoTeC M1 here. And before we get started with that, I'll just talk you through what we're going to do. So if we jump back into our MoTeC software here on the laptop. Now the M1 ECU that we've got installed on our Toyota 86 gives us one reasonably big advantage. I'm going to be able to actually show you two things here, because the FA20 engine in the Toyota 86 uses a combination of both port injection and direct injection. So I can choose what level of injection is going to be delivered by the port injectors and what's going to be delivered by the direct injectors, which are obviously inside the combustion chamber, and we can vary that mix to do whatever we want, and then we can also control the injection angle individually of both injectors. Now what we're going to do is I'll just start the car, and generally, because we are not original equipment manufacturers and we're more interested in performance than we are in emissions. Generally, as performance dyno tuners, we generally have a wideband air fuel ratio meter that we use for our tuning. So we're only really looking at that single aspect of the exhaust gases, which is our lambda or air fuel ratio number. If we were tuning for emissions, or an original equipment manufacturer would do, we're actually going to be using a 5-gas analyzer, and some of those other aspects such as oxides of nitrogen, etc., hydrocarbons, unburnt hydrocarbons, those will also be influenced by our end of injection angle too. So for this particular demonstration, what we're going to be looking at is simply the effect that the injection angle has on both our lambda value, air fuel ratio, and also the torque, because really those are the two things we're most often going to be faced with as when we're doing performance engine calibration work. Okay, so what we'll do is I'll just talk you through what we've got here in the MoTeC software. So this first table here that I'm going to just open up is our secondary injector contribution table. So basically this defines how much fuel is being delivered by the secondary injectors, which in this case are the port injectors. So what we're going to do for the demonstration is we'll run the engine at 3000 RPM, and you can see what I've just done there is highlighted that section of the graph of the table and entered a value of 0 everywhere. So basically everywhere below 3000 or 3000 RPM and below, the engine will be running solely on direct injection. Okay, so that's one aspect of it. Now let's also have a look at, I'll just get this a little bit smaller. Let's have a look at, we've got also our engine efficiency graph, which is where we actually program the engine's volumetric efficiency. So we program this to achieve our aim lambda value. So that's going to become important shortly. And then lastly, we've got our fuel injector timing. Okay, so when we look at the fuel injector timing in the MoTeC M1, you can see that we've got fuel timing secondary and fuel timing primary. Now the primary, remember, that's our direct injectors. The secondary, that's our port injectors. So what we're going to do is we're going to break the operation down, and we're going to treat this engine first of all just like a complete DI engine. We'll forget about the port injectors, and we're going to look at how the injection timing can influence torque using DI. And then what we're going to do is we'll convert it so it's running 100% port injection, and we're going to look at that aspect of it. Now at the same time, if Ben's got the dyno graph, screen being visible as well, the two areas we're going to be looking at here, we've got our lambda value, and for this demonstration we will be tuning in units of lambda, and then to the right we've got our torque, which is the feedback we're going to be using. So what I'll do is we'll just get the fan turned on the dyno so I can run the car, and we'll just bring the car up to 3000 RPM. So what I'll do, it's just basically like tuning any other element of the the mapping. We need to make sure that when we're adjusting the end of injection angle, that we're in the middle of a zone. So what I'm going to do is just bring up a target. Okay, so you can see we've got this little target here which will tell us when we're in the middle of a particular zone. So at the moment, if we look at the dyno, you can see that we're running at about 0.98 lambda, and we're producing about 80 Newton meters of torque. Actually what I'll do is, I'll just change this so we've got a little bit more multiplication on our graph here, so it's a little bit easier, and I'll use axle torque. Okay, that's just going to make the numbers a little bit larger because we're now multiplying the torque by our final drive. So you can see we're sitting there at about 399, 400 Newton meters, and what I'm going to do at the moment, you can see the value in that particular zone of the table is 255 degrees. Now obviously when we're talking about direct injection, really the intake valve opening is irrelevant because we're injecting fuel directly into the cylinder. And depending on the particular strategy of the ECU, we can often see direct injection engines using 1, 2 or 3 injection pulses during the engine cycle. Now, one of the advantages with DI is it can remove a lot more heat from the combustion charge, and that helps reduce the heat in the combustion chamber. Two advantages of that: because it reduces the heat, it actually improves density. It can have a very small improvement in engine volumetric efficiency. The other advantage is because it's removing so much more heat than a conventional port injection engine, we can also generally run a higher compression ratio and more ignition time, and the engine's not so knock limited. And a lot of that comes down to whereabouts in the engine cycle the direct injection pulse is occurring. The advantage, or the reason why DI can do this, is because in a conventional port injection engine, when the fuel is injected, a lot of it's going to end up absorbing heat and going through its phase transfer from liquid to vapor. It's going to be absorbing heat from the port walls, the cylinder head and the back of the valve before it finally makes its way into the engine. Is where the advantage in DI comes from, and that is in that the fuel can be very accurately controlled on where it's delivered inside the combustion chamber, and that means less of the fuel is going to be drawing heat from the piston, from the walls of the cylinder and the combustion chamber, etc. So a lot more of the phase change is actually being used to draw heat out of the intake charge. Okay, so that's enough of the theory. Let's have a look at where we were again. So we're sitting at this particular pressure point here of 60 kPa, I'll just get rid of the graph, 60 kPa and 3000 RPM, and at this particular point the end of injection angle is 255 degrees before TDC. Again, you can see we're sitting at about 395 foot-pound newton-meters of torque, about 400 newton-meters of torque. Now, just like making any change, let's compare it to changing our ignition timing. What we're going to be doing is making a change to our end of injection angle and seeing what that results in terms of a torque change. So for a start, let's change that to 245 degrees. So we're taking 10 degrees out of it. Now, the DI side of things makes it really easy to actually do this testing, because we do see quite significant changes. So you see there, we basically just dropped off 20 newton meters by changing that injection angle from 255 to 245 degrees. So let's just go a little further just to prove the point. We'll change it another 10 degrees to 235 degrees. And again, you can see we dropped off almost the same, probably about another 10 or 15 newton meters. Now, the whole time I've been making those changes, the lambda value hasn't actually changed. We've been sitting pretty consistently around about 0.98 to 0.99 lambda. So let's go back to 255. Okay, so our lambda hasn't changed, but we are seeing changes in our engine torque. So what we're trying to do is optimize the injection timing to simply achieve maximum engine torque. We're going to look at another aspect of that when we deal with the port injection. So let's try going the other way. Let's go to 265 degrees. So we're sitting currently at 400 newton meters. Okay, with that change we've gone up to 412 newton meters. So it's a very small gain, but we have seen a gain. So let's try going a little bit further. Let's go to 275, and we'll enter that in. You can see we've actually gone backwards. What that means is we were pretty close to the correct point before, but we definitely see an advantage from setting that injection end angle to 265 degrees. If we want, we can try breaking that down and going to smaller changes to 60 degrees or 265. We are really chasing very minuscule gains. So once we've optimized that, basically we would just adjust the injection angle slowly but surely in 10-degree increments until we've achieved our maximum value for that particular zone, and then we'd simply step up, just like tuning ignition timing, and we'll move now into the 80 kPa row. And let's just tune this zone as well, and we'll just see what the effect on our torque is. So I'm stable in the middle of that zone, and we've got 235, 240 Newton meters. Let's try taking 10 degrees out. I'll try doing it the correct way. Okay, with that particular change, you can see at this point we're getting quite a lot of fluctuation in our torque. I'm just going to add 10 degrees back in again. It looks like if we read between the variations we're seeing in our torque, I think with the 10 degrees out of it at 212, we are seeing a very small improvement on average. What I'm just going to do is bring back my target, which I just managed to delete, just to make sure I am in the middle of the zone. Again, remember when you're tuning things like this where we are looking for quite small incremental improvements, it's really, really critical that we are right in the middle of our tuning target. So you can easily vary the torque much more dramatically than the result we'll get from the injection timing, simply by moving your foot on the throttle. So let's try adding 20 degrees into there. We're sitting at about 540, 550. So we'll add 20 degrees in, and we've picked up a little bit there. We're up to 560. I'm going to add another 10 degrees in there. Okay, so now we've gone up to 570, 580. So that looks like we're moving in the right direction. We're getting a noticeable change. We'll add another 10 degrees. Okay, so again, we've had a positive result there. So we've gone up to 580, 590. So again, I'll add another 10 degrees. Okay, so this time we've gone backwards. So we'll take that 10 degrees back out. So there's a very noticeable change, and you'll find that direct injection tends to be quite a lot more sensitive to the injection angle than port injection, and we'll see that in just a second. But in that particular change there, we've picked up from about 530 Newton meters to 580, 590. So 50 odd Newton meters, we're getting on towards a 10% change in our axle torque. So it's not an insignificant change, and there really is value to be had in adjusting our injection angle. Okay, so now what we're going to do, as I said, we'll just jump back into our secondary contribution table. And what I'm going to do now is set those same rows, same zones that we were running in, to 100% port injection. So now this, in a really simple change like that, converts our engine into a conventional port injection engine, much like you guys would be used to seeing. So now if we jump back into our fuel timing, now what we want to look at is our fuel timing for our secondary injection. Now hopefully this is going to show us another aspect of our how the injection angle can affect our fuel delivery. So let's just get the engine running, and again what I'll do is I'll start with just the bare minimum amount of load on the engine. We're in that 60 kPa row. Now what we'll do for a start, because we're actually now with that particular change we are quite lean, so I'll just get the lambda back into target. So we're sitting on our target there of 0.98, 0.99. I'll just make another little change there. Just get it as close as we can to lambda 1, and I'll just do the 70 and 80 kPa rows as well, zones as well, just so when we go and change those we're already going to be on target. Okay, so that's got those three sites correct. So now let's go back to our fuel timing and we'll go back to 60 kPa. Now you can see the number that we've got in there to start with is 450 degrees. Now remember, depending on the exact cam profile and when the cam's opening, that should have us injecting probably against a closed valve. So again, we're looking at the same aspects. We've got lambda and we've got our axle torque, and again we're sitting at 400 Newton meters. So what I'm going to do, just dramatically, I'll just do the whole row. So let's change it to 300 degrees. So we'll go for quite a large change. Okay, so what you can see there is we have picked up a little bit of torque. We've gone from 400 up to about 415. Actually, I'll just get back into there. About 410 Newton meters. So we've picked up a little bit of torque there. What I'll do, I will actually just make a smaller change. So let's try 200 degrees and see what effect that has. Okay, so now we've got two things that have happened there. Again, we've picked up a little bit of torque, just about 5 to 10 Newton meters. What we also did was we're now operating a little bit richer than we were. Remember, we were operating originally at lambda 1, and what happens generally as you move towards the ideal or a better end of injection angle, as you move closer towards that ideal angle, what's happening is more of the fuel is being delivered into the engine in a combustible form. Now the actual injection pulse width, the amount of fuel being delivered, that hasn't changed at all. So what happens is as we move to a point where the engine's working more or using that fuel more efficiently, two things happen. First of all, we see a small increase in torque, and the other thing we see is that our air-fuel ratio will start to move a little bit richer. And that wasn't very dramatic. We only moved about 1 to maybe 2% richer, but you saw we moved from lambda 1 to about 0.98, 0.99. So what that means is this is where the gain comes in, because now what we can do is we can go back into our main fuel table, and we can then, or in this case our volumetric efficiency table, and we can remove some numbers from that volumetric efficiency table. Now what that's going to do is get us back to our target air-fuel ratio, in this case lambda 1, but the injection pulse, the amount of fuel being used to achieve that particular target is now going to be less. So in essence, the engine's operating more efficiently, it's using less fuel to do the job. So let's just go back to our operating zone there again, and what we're going to do, just to show you the effect of this, we're going to just make some more changes to this. So we're sitting at our 60 kPa row now, 420 Newton meters, and we've got a end of injection angle of 200 degrees. Let's try, in this particular case we're actually limited to 120 degrees before TDC. There's a limit in the MoTeC firmware. So we'll enter that, and before I do that we'll just get back so we're running at a consistent torque. So we're back at our 420, 430. I'll press enter. You can see if anything we've gone backwards marginally, but the gains we've made, the change we've made there is very, very small. So let's go back to the 450 that we started with, and you can see that our torques dropped back to 400 Newton meters, which is where we were. Okay, so hopefully we'll shut off the dyno fan and just have a bit of a chat about the results we've seen there. The process of tuning our injection angle is just a case of repeating that for each particular site in our table. Now if we look again at our laptop software here, you can see that what I've got set up at the moment is a three-dimensional table for that fuel timing, and it's relative to inlet manifold pressure and our engine RPM. Now you can simplify your life, and a lot of ECUs don't give you the option of having a 3D table in there. A lot of ECUs will only give you the option of a 2D table, and to be honest, that's probably just fine for port injection. We don't generally need the precision, and you can see here at the moment, this table is set as if it's a 2D table anyway. All of the numbers are the same regardless of the manifold pressure. So in the MoTeC, we could simply go through and disable our inlet manifold pressure axis, and this gives us a 2D table, which is what we would see in quite a lot of other ECUs. The other thing I wanted to talk about with the port injection timing is, if you really want to try and get the most out of your injection timing, clearly you do need the ability to move around the injection pulse, the position of the injection pulse in the engine cycle to some degree. Down at 3000 RPM or at idle, where we've been doing this test, that's quite easy because the size of the injection pulse, the injector duty cycle isn't that great. So we can vary the injection timing significantly, and we can measure the results of that change quite easily, which you've seen on the dyno. Clearly though, if you do the math, if you are getting up to 7000 RPM wide open throttle and your injection duty cycle is sitting at something like 85 or 90%, at that point there's clearly going to be little to be gained by moving around the injection timing. Simply put, the injector's pretty much open for the entire injection cycle, the entire engine cycle anyway, so there's very little opportunity to actually move it around and gain some advantage. In classes which are particularly restricted on their engine specifications, and really they're trying to use every trick in the book to optimize engine performance and engine torque, in those classes injection timing can play a role in improving the engine performance. Now in those classes, the injectors would be sized accordingly. So they're going to be sized so that at wide open throttle and maximum RPM or maximum duty cycle, we're only seeing somewhere around about maybe 60 or 65% and injection duty cycle. Now that means that we do still have the opportunity, even under high RPM and high load, we've still got the opportunity to make a reasonably significant change to the injection angle and see if we can get an improvement or a gain from that. So that covers how we as a performance tuner would look at optimizing the injection angle. And let's be honest, most tuners probably don't even bother adjusting that table. It's kind of left at whatever default values the ECU manufacturer put in there when it was shipped out, whatever firmware you're running, and that's the last people really think of it. It does start getting towards the sort of pointy end of smaller sort of microscopic changes in our torque and our engine performance, but you know, if you've got the time to devote to adjusting that table and really noticing the difference in torque, then there can be some advantages in doing so. And the other thing is, as our injectors get bigger, particularly if you're running very large injectors on a small engine, down at idle and cruise, you can get a reasonable improvement in fuel economy and torque from moving the injection angle around. Alright, so what we'll do is I'll jump back in now and see if you guys have got any questions. If there has been anything that's cropped up while I've been talking, feel free to continue to ask those questions, and I will do my best to get to them as soon as I can. Okay, so I'll just make that a little bit bigger so I can actually see it. MoTeC said you have to be careful with the timing on a DI system, as injecting too early in the engine cycle will turn the injectors into a water cutter on the top of the pistons. Yeah, definitely the injection timing with a direct injection system is much, much more critical than port injection. I mean, with port injectors, it doesn't really matter. You can inject against a closed valve and the fuel's just going to sit there until the next engine cycle comes around, and then it'll be injected into the engine. With direct injection, we can literally time the injection event to happen whenever or wherever in the engine cycle we want. So there is some care required. Most of the time when we're tuning a DI engine, for the most part, it's probably going to be reflashing a stock DI engine, and in that case we've already got the manufacturer's sort of starting point to work from, and chances are they're also going to be pretty close to the mark. You can see what we've done there with the DI timing on this particular engine. We moved it around about 20 degrees, so you quite quickly see if the changes you're making are a positive or having a negative effect. So if you're starting to see the torque drop off, and when I did that with the DI, we only needed to move about 10 or 15 degrees before we actually started to see quite a sharp drop off in the engine torque. So obviously we're going the wrong way, move back, go the other way, and it's pretty easy to find the optimal point. But definitely you don't want to be going and making wholesale changes to the injection angle, because that definitely can be dangerous. Rotate said any gains to be had in rotary applications. Default on the ECU's 360 degrees. Now look, again, just to reiterate with this, it doesn't really matter what your engine is, whether it's a rotary or a piston engine, how many cylinders it's got, how many valves it's got. The principles still remain the same. What we're trying to do is control when the fuel's delivered, so it's delivered into the engine at the optimal time. So obviously a rotary engine doesn't have valves, but it definitely still does have port timing, so that aspect still works in a similar way. And again, the actual timing is not particularly relevant. The numbers in those timing tables, they're 360 degrees, for example, before TDC. It doesn't really matter. What we can do is simply make an adjustment to that injection timing. Maybe start by making 50-degree changes and see what the measured torque difference is when you make that change. You're quickly going to be guided in the right direction by what the dyno tells us in terms of the engine's torque production. Dave said, Andre, does the 86 have a separate DI control module and the M150 controls that, or is the DI controlled directly by the M150? The 86 is quite unique in that it's got an external direct injection amplifier, so the M150 is actually controlling that, much like it would control a conventional port injector. So the amplification to control the direct injectors is done by a separate module. David said, have you played with the injector timing on the GM E38 VE to VF LS1 controller with big cams? To be perfectly honest, David, no, I haven't. And we have done some VE to VFs with reasonable size cams. Again, it comes down to how much time you've got available, and obviously these start becoming incrementally smaller gains. So this would be the sort of stuff you're doing when you've got everything else nailed, you've got your fuel delivery on target, you've got your ignition timing table sorted, and that's all running correctly. And then if you've got time, then you can start playing with your injection timing. Of course, with a factory ECU, that factory calibration for your injection timing is already going to be probably a lot more thoroughly calibrated than the likes of what we see in a blank, freshly installed aftermarket ECU. So the starting point with the GM LS V8s is already going to be better than what we're normally going to expect to see. Max Booster said, does the Link ECU have a specific map for tuning injection timing, or does it only have a single setting? No, there is the ability to control the injection timing with the Link ECUs as well, depending of course what generation of Link ECU you're talking about, but definitely on the G4 and the G4 Plus we can do that. I might, if I've got a chance, I might pop into the software shortly and we can have a look at those settings for you. Rotate said, as we're staged as well, primary and secondary injection time will end up different to each other in terms of the distance to the port. Yeah, absolutely. The actual location of the injector relative to the intake valve or the port entry in the case of a rotary also has an effect on what the ideal injection timing will be. Depending again on the particular ECU you're running, a lot of ECUs that have staged injection capability will have a separate injection timing table for both the primary and the secondary injectors. So again, all of this starts coming down to we're getting incrementally smaller and smaller in our gains or our advantages in doing so, and really it comes down to how thorough you want to be and how much time you want to spend on the dyno plugging away to try and get the absolute last sort of amount of power and torque out of our engine. Okay, so what I'll do now, I'll just go through to a base map here in our Link G4 Plus software, and if we look in our fuel table, sorry, just give me 1 second. Okay, so we've got our fuel set up and we've got our injector set up. Now I'm actually going to get myself massively lost here. Fuel injector timing, right. Okay, so this is the setup that you've got available in the Link G4 Plus software. So this depends again on how fussy you want to be. So at the moment, the setting we've got here is single zone. So that's literally the injection timing is fixed at one particular point, which you can see here, I'll just get rid of that again, is 330 degrees. Again, remember at the start I talked about the injection timing being either end of injection or start of injection. With the Link, as with some ECUs, you can alter which particular point in the injection cycle we're timing off. So the Link gives us the option of start of injection, end of injection, or even center injection if we want. Then we can create a table, and that's going to create a proper injection timing table, which we should be able to access. And in this particular case, you can see that this is only a 2D table. You know, as I explained, there's probably with port injection the gains to be had by doing a 3D compensation table, probably not really worth the added hassle. Alright, so if there's any other questions, feel free to keep putting them in here. I'll just jump back. Heltech Mitch has said, Andre, do you find different fuels require different injection angles? Look, to be perfectly honest, Mitch, my testing has not been that thorough or that in-depth. And again, I've said it a few times now, we really are talking about incrementally smaller advantages from tuning that end of injection timing. I can't say that there wouldn't be gains by changing the injection timing for different fuels, but if there were, I would imagine they would probably be starting to get fairly microscopic by that point. Okay, that looks like it's the end of our questions. Doesn't look like there's anything else there. If you do have anything that crops up after the webinar finishes, please feel free to put them into our forums and I'll do my best to answer them in there. In the meantime, remember, if you do have any suggestions for course material, any courses that you would like us to consider producing, please feel free to flick Ben an email, ben@learntotune.com, and give him your list. You never know, your favourite course might end up being next on our list. The other thing we'd really love, this is going into our new website, if you've got if you've been a HPA member and you really like what we're doing, you feel that we're producing good content and you're getting great value for your involvement with HPA, we'd really love to hear about that. So again, please flick us an email, ben@learntotune.com, with a testimonial. Those would be really handy for our website and we'd really appreciate it. Okay, one other thing I forgot to mention, and again, you guys are all our ProTuner members, so you've got ProTuner membership for life. You're never going to pay for that. We said at our last webinar that from the beginning of this month, with the launch of our new website, the ProTuner membership was going to be a paid subscription membership, which is still our intention. We're going to extend that out for another month until the launch of our website. As I said, you guys are all getting this for free anyway. You are already ProTuner members, but if you do have any friends out there in the tuning world, any mates that you think would benefit from our courses, this is the time to send them our way. Any courses purchased before the end of November are going to get that free ProTuner membership for life. Alright guys, we'll leave it at that. Thanks again for joining us, really appreciate it.